Hey, welcome to the next lecture. I believe this is lecture 4 for the SheQuantum organization, which is an organization that's supporting women in research and learning of quantum information science. This is a lecture series about entanglement theory. In the last lecture, we talked about the tool of partial trace and purification and its interpretation. Okay, so this lecture, we're going to move on to the concept of a quantum channel. And the basic thing that you need to understand is a quantum channel is a physical evolution of a quantum system, right? So in quantum computing, if you have a circuit that evolves one state to another to get from some initial configuration to the final output of the computation, that is in fact a kind of quantum channel, okay? If you perform a measurement on a quantum state to read out the outcome, to read out information from the state, that's a quantum channel. And in fact, it goes further. Essentially, everything that's a physical evolution can be described as a quantum channel. Okay, and you could even consider that to be the single basic postulate of quantum mechanics, that everything is a quantum channel. Okay, so before we get into quantum channels, let's talk about what are classical channels. So they model the evolutions of classical systems. And what are the requirements that we make for classical channels? Okay, first of all, they should be linear maps. Okay, so why is that important? If they're linear maps, it means that they respect convexity. So this is kind of a sensible thing, right? Suppose that a classical system is in some state, and then you apply the classical channel. There will be a particular probability distribution, okay, for the output. Suppose the input classical system is in a different classical state, and then you apply the channel, then there will be a different output probability distribution, okay? Then you would expect that if the input system were in a mixture of the two possibilities, right? So with some probability, it's in the first state, and with another probability, it's in the other state. You would expect that when you apply the channel, the output would be the mixture of the individual outputs. And so that's what I mean by respecting convexity. It's something very sensible that you would expect not only for classical systems, but also for quantum systems. So linearity will be a requirement for quantum systems as well. Okay. Another thing for classical channel is it's very simple. You would expect that if you input a probability distribution to the channel, the output should be a probability distribution, right? So they should output a legitimate state. So these are like mathematical requirements for a classical channel. Okay. And so you put together these two basic requirements that we would expect, and then you can conclude from that. We won't prove it, but there's a way to prove it. These requirements imply that the evolution of a classical system, it's specified by a matrix, and that's called a conditional probability matrix with these entries. It has two entries. One is for the output, one is for the input. And then the input-output relationship is given by a matrix equation, right? So a matrix vector equation. This is a column vector, this is a matrix, this is a column vector. And that's the same as writing things out in the index notation, right? So the output probability distribution is given by the matrix vector product of the channel matrix with the input probability distribution vector. Okay, quantum channels, they model evolutions of quantum systems. And for the same reasons that I stated previously for the classical case, we demand that a quantum channel be a linear map. Okay, so that means it'll respect this convexity. So if the channel acts on a probabilistic mixture of density matrices rho and sigma, the output will be the probabilistic mixture of the individual outputs. So that's what convex linear corresponds to, and then more generally, we just demand linearity. Okay. We also demand, similarly as we did in the classical case, that a quantum channel should take a quantum state to a quantum state. That's the basic requirement that we demand mathematically. Okay. So one thing that it means is that the channel should be trace preserving, right? So the trace of an input matrix should be the same as the trace of the channel acting on that input matrix. Okay. Another thing is something that's called complete positivity. So this is something that's unique to the quantum case. It's not of importance in the classical case, but it's very important in the quantum case. So let's describe what this means. Suppose we have a bipartite input density operator, okay? Then you can use an orthonormal basis for the reference system to expand this operator in this way, where we're saying like, we're writing the reference system with respect to this orthonormal basis. And then these are matrices that depend on the indices I and J. So that's always possible to do that. And then what we're going to do is define the channel tensor with the identity acting on this matrix. And we define it in this way, such that it's linear. So it can go, identity and n can go inside the sum. The identity does nothing to this reference system, and the channel gets applied to each of these matrices. Okay. So if we were to sort of step back and think about this in a physical sense, we can think that system R belongs to Ramanujan and system S belongs to Sam, okay? And so on Ram's system, nothing's happening, but on Sam's system, the channel is acting, okay? So that's a way to think about it. And it's important to think about this because you can have that situation in physics, right? Where like Ram and Sam possess a joint quantum state, but something is only happening to Sam's system. So that can happen. And then what we demand is that the output of this evolution give a legitimate quantum state, right? So this is the requirement of complete positivity, that if the input density operator, if the input operator is positive semi-definite, this output should be positive semi-definite as well. And so that corresponds to requirement 2. A quantum channel takes states to states, right? And so every density operator is a positive semi-definite matrix. So the output of the channel should also be a positive semi-definite matrix. And then if it's also trace preserving, then, you know, if the input operator has trace 1, the output operator will have trace 1 also. So the output will be a legitimate quantum state. So if you have a mathematical map that satisfies all these requirements of linearity, trace preservation, and complete positivity, then it will take all density matrices to density matrices, and that's what we call a quantum channel. So that's the definition. All of that was a bit of a mouthful. If you want to check whether a given map is completely positive, you might think from the definition of complete positivity that you'd have to check this condition on an infinite number of operators. Fortunately, it's not the case. It suffices to check the action on a single input, and that's what we call the maximally entangled state right here, which is related to this QET, which is defined in terms of this QET in this way. This generalizes the Bell state. The Bell state is what you get if D equals 2. If D is larger than 2, then you have this, I guess we call it maximum entangled QET state. Okay, so this is something that you can check in MATLAB if you have a map. And I should probably mention there is a package of MATLAB called QET Lab. So it's QET Lab. And I think it stands for quantum entanglement. I'm not sure. Maybe it's something else. But it has all these functions that you can play around with in MATLAB to check these properties of quantum channels. Okay. There's an important theorem for the quantum case, which says that every quantum channel, as we said, that means that it's linear, trace preserving, and completely positive. Every quantum channel can be written in this way. So what we talked about previously might have seemed like an abstract concept. This is a more definitive method of writing down a quantum channel. So you'd have a set of matrices. Their size doesn't matter, right? And what you do, well, it should be a dB by dA matrix where dA is the dimension of the input and dB is the dimension of the output. Okay, so X should be a dA by dA dimensional matrix, and then this Ki can act on that and produce an output. So what you do is you sandwich the input operator by the Ki and Ki dagger, and you sum over all of them, and then that gives you the output of the quantum channel. And so these operators, they're called Krauss operators after one of the inventors. If you square them and take their sum, that should be the identity operator. And then that guarantees that the map will be trace preserving. That's a simple calculation you can do to check that. And the fact that you have Ki and Ki dagger ensures that the map is completely positive. Okay. This is not necessarily a minimal, or it's not necessarily a unique decomposition, but you can find what's called a minimal decomposition, such that you're minimizing the number of operators needed. If you take the spectral decomposition of the channel acting on one share of a maximum entangled state, that's a density operator. If you diagonalize it from the eigenvectors, there's a way you can extract the Krauss operators. Okay. As a particular example, and this is the example that's most prominent in quantum computing, is a unitary channel, right? So if the channel just has one Krauss operator, then that one Krauss operator has to satisfy this condition. So that's just that U dagger U is the identity. And if a matrix satisfies this, it could be a unitary. More specifically, it's called isometry, isometric matrix. But that's what comes up in quantum computing is unitary matrices. So what do we know about unitary channels is that they're ideal, like there's no noise involved, and they're also reversible. How do you reverse? You just do U dagger. You go back to where you started. So in quantum algorithms, you have these instruction sequences that tell you how to execute the algorithm. And in principle, those are composed of ideal unitary channels. In practice, it's very different from that. Okay. So this gives you a way to check that, well, if a channel has more than one Krauss operator, then it's non-unitary. If you do this minimal decomposition and then you find that there's more than one Krauss operator, it's non-unitary. Another kind of channel is a measurement channel. So that takes a quantum system as input and produces a classical system as output. And we can describe that in the language of density operators and quantum mechanics in full in this way. So if you have a set of matrices, each of which is positive semi-definite, and their sum is the identity matrix, you can use that to construct a measurement channel. So in comes a state rho. You take the trace of one of the operators with rho, and then place that along an element of the diagonal of the matrix, right? That's what these x's are, is they correspond to diagonal elements. And then you sum over all of them. That's a measurement channel. And the interpretation here is that you get the classical outcome x with probability trace mx rho. Okay, so that this formula here, trace mx rho, is a famous formula called the Born rule of quantum mechanics after Max Born. This is what we were just saying a minute ago, that a measurement channel returns the classical value x with this probability. And then if you look in in the literature or textbooks on quantum information, this is how we depict measurement channel. The quantum system comes in, there's like this dial that's telling you the classical outcome, and then the classical outcome is placed on this line here. Okay, let's see. So why don't we say quickly, what is a quantum instrument? Because we'll need that concept when we've defined LOCC. And then that'll be the last concept for this lecture. So a quantum instrument, it's a kind of channel that has a single quantum input and two outputs. One of them is classical and one of them is quantum. Okay, so this is useful when you want to describe evolutions where you do a measurement, but there's also a post-measurement state, right? So an example would be in optics. You could send in a photon into a beam splitter, right? And then the beam splitter would split the light beam into two directions, one going orthogonal to the original direction and one going in the same direction as the original direction. And then you could put a photodetector at the output of one arm of the beam splitter. And so the photodetector would give you the classical outcome of the measurement, is where in the other arm is propagating a quantum state that's in the post-measurement state. Okay, so that's an example. So in this kind of quantum instrument, you're recording not only the classical data, but also keeping the post-measurement state. Mathematically, you write it like this. So you have a set of completely positive maps, such that the sum map is trace preserving. And here is where there's the quantum output, the post-measurement output, and here's the classical output. Okay. And the interpretation is that the probability of obtaining outcome X is given by the trace, this trace expression here, and the post-measurement state is one of these maps. If you get the outcome X, then the post-measurement state will be one of these maps acting on rho divided by the probability of getting that outcome. All right, let's stop for now. We'll pick up the next time.